Okay, so for the first one, reducing these algebraic fractions with the variables in them. We separate out the numbers. If I reduce the 12 over 8, what's that going to reduce to? 3 over 2. Good. So we can do the numbers separate. Now remember, we do not change the numbers into an improper fraction. We're just going to leave them, or not, sorry, we don't change them into a mixed number. We're going to leave them as improper fraction because we don't know if that splits up into 1.5. We don't really know if the numerator is bigger than the denominator because we have the variables up there. Now what's going to happen with the variables? X goes on top because it has the larger power of the 2. And what's its power going to be? Just going to be x, because 5 minus 4 is 1, so x to the 1, or just x. How about d? Bottom, and what power? 3, d to the third. So that fraction reduces to 3x over 2d to the third. Any questions? Okay, the other one. 4 over 16, that's going to reduce to what? 1/4. Both divided by 4, 1/4. So 1 on top, 4 on bottom. What happens with the a? Goes to the bottom, and what power? The 2. The larger power of a was the 5 on bottom, so it goes on bottom. 5 minus 3 is 2, so a to the 2. What happens with the d? Cancels out. D to the 5th divided by d to the 5th cancels out. It's 1. So it doesn't have to go on there. So 1 over 4a squared. How many people had those first two right? Any major questions on those first two? You look a little scared over there. Okay. Does it make sense? Okay. Hopefully it'll get better as we go on. Finding a common denominator, we didn't do a lot of this, but if I have 10x squared and 6x to the third, the way we went about that was factoring. So 10 factors into 2 times 5 times x. 6 factors into 2 times 3, and then x to the third is just 3 x's. And we look at what they have in common first. Well, they both have a 2, and they both have 2 x's. Well, then we look at what they don't have in common. What's the top one missing? A 3 and an x. So I'm going to multiply by 3 and x on top. What's the bottom one missing? The 5. So multiply by 5. So of course this here is just the 10x squared. So 10x squared times 3x is 30 x to the third. Again, this here is the 6x to the third times 5 is 30 x to the third. And we do need to get the same thing for both of those. So that's telling us that 30x to the third is our least common denominator. How have you had that one right? Good. Any questions on these? We will come back to these and go over them more as time goes on.
So I know we just had to find the common denominator, but to find the top number,
okay.
Take like the 5 times 6, right?
Yep. Yeah, so the 10 here was multiplied by the 3x. So that means we're multiplied by 3x on top and bottom of that one. So that's one's going to be 21x over the 30x to the third. And then this one we had to multiply by the 5, so multiply by 5 on top and bottom. So yes, 25 over the 30x to the third. Yep, perfect. Any questions off the homework from last class? Doing good? So far. Today we're going to take a little bit of a different approach. We're going to look at ratios today. One of the things we're going to look at is ratios. A ratio is nothing more than a comparison between two numbers. For example, we might look at students enrolled here in Rice Lake compared to students enrolled over the network. Right now, I have 8 students enrolled in Rice Lake and a total of 12 students enrolled over the network. So I can write it like this as a fraction, 8 to 12. I can write it as, with a colon in it like this, 8 to 12. Or I can write it out in words. In this case, I would write it 8 to 12. Writing it in words, you have to be careful because there's two possible ways you could word it. There's 8 to 12, or you could word it as 8 out of 12. In this case, the 8 to 12 would be appropriate, and the 8 out of 12 would not. And I'll explain why that is so in just a little bit. For right now, let's look at what we can do with these ratios and stuff like that, and expressing the ratios. I like the fraction notation, 8 over 12, because in that notation, we can do a lot of things with our ratios that we can do with a fraction, like reduce. Both 12 and 8 can be divided by 4, which gives me a 2 to 3 ratio. Now we can do the same thing in this notation. We can divide both the 12 and 8 by 4. It gives me a 2 to 3 ratio. It's just we're used to doing it as the fractions. It's natural for us. So it's not really a new thing for us to do it in that form. The big thing, just like with our algebraic fractions, is we cannot make those into a mixed number. They must stay as just a fraction, because the ratio is just a comparison between two numbers. So 2 students in the classroom here in Rice Lake compared for every 3 students that are on the network, is what that's saying. I might do a ratio of one of these tables here. I mean, it looks like we have pretty much the same tables in your classrooms. The tables here are 18 inches wide, and they're 6 feet or 72 inches long. So I got a ratio of width to length of 18 to 72. Now the inches can cancel out, just like an x would cancel out if they were there. And both 18 and 72 can be divided by 18, which gives me 1 to 4 ratio. First thing you'll note is in both of the 2 examples I did so far, the 2 numbers I'm comparing have the same label. This was 8 students to 12 students, or 2 students to 3 students, if you want to put it that way. Yeah, there's something that separates them. In this case, it was location, but it's still students compared to students. Down here, it was 18 inches compared to 72 inches. Yes, one was width and one was length, but it's still comparing inches to inches. That's one of the qualifications of a ratio, is it must compare 2 things with the same units. Because of that, the ratio itself, once it's simplified, has no units. This 1 to 4 ratio of width to length doesn't matter what the units are. If I'm looking at that table, doesn't matter whether I'm talking about centimeters, inches, feet, yards, meters, or whatever. That's just saying for every 1 unit of width, there are 4 units of length. So it could be 1 inch of width, there's 4 inches of length. For every 1 centimeter of width, there's 4 centimeters of length. For every 1 foot of width, there's 4 feet of length. Doesn't matter what units. So then we can run into something like this, where maybe we're comparing 2 feet to 18 inches. Well, right now that's not a ratio because we're comparing 2 things with different labels, different units. Fortunately, I can change that. 2 feet can be changed to 24 inches. Now, 24 inches to 18 inches does have the same units. It is a ratio. So the inches will cancel out, just divide out, like if that was 24x and 18x, the x's would divide out. 24 and 18 can both be divided by what? 6. 24 divided by 6 is 4. 18 divided by 6 is 3, so 4 to 3. Now again, I'm not going to reduce that to a mixed number. I'm not going to make it 1 1/3. I can't do that. This is 4 to 3. It's got to stay like that, look in that appearance of an improper fraction.
Well, instead of changing the multiplication,
You could have made the 18 inches 1.5 feet, so then it'd be 2 to 1.5. Then you could simplify it that way. Yeah, it's still gonna come out 4 to 3, by the way. You'll notice I've been using that term 4 to 3 or 1 to 4. When we're talking about ratios, there's 2 types of ratios. In the 1 type of ratio, I'm comparing the amount in part A to the amount in part B of something. And that's what I'm doing here. This was a length to width. So the units of width to the units of length. Or I could be comparing the amount in part A to the whole amount. Or the amount in part B to the whole amount. In this case, I used the term 2. 1 to 4, 4 to 3. Here I would use the term out of. So let's go back to that first example of a ratio I did, where I had two students in Rice Lake to every 3 on the network. This would be a 2 to 3 ratio. But I could have said 2 students in Rice Lake out of 5, every 5 total. So this would be 2 out of 5. Believe it or not, these 2 ratios are expressing the exact same relationship. Because when we have ratios, usually there are, especially ones like this where it's 2 out of 5, there are 3 ratios implied there. If I'm stating there's 2 students in Rice Lake out of every 5 students total, this is the whole amount or the total amount down here. First of all, I'm applying the ratio that then the other 3 out of 5 are where? On the network. So if there's two students in Rice Lake out of every 5 total, there's 3 students elsewhere or on the network out of every 5 total. And then, of course, we've got the 2 to 3 or 3 to 2 ratio, depending on how I want to do it. I do Rice Lake to everybody else, or I could do everybody else to Rice Lake.
So if you divided out 2 to 3, you pass the complete.
Yes, yes. When it's listed like this, yes. So for example, let's say we're mixing up a solution. In the medical field, we do a lot of medications dissolved in water. So let's say we're going to mix 4 milligrams of medication in, let's word that correctly, 4 milligrams of medication with 12 milligrams of water. There are 3 ratios, important ratios I can give here. Actually, probably 4 actually I could give here. I can give the ratio of medication to water. What would that be? There you go. 4 over 12. I can put the milligrams with it if I want to. They're going to divide out, and that's going to reduce to a 1 to 3 ratio. So 1 part medication to every 3 parts water. I could flip that over and do a water to medication. That's just going to be what? 12 over 4 or 3 to 1. Those 2 are basically the same ratio. They're just reciprocals or flipped over. I could then do ratio of medication to the total amount of that solution. How much medication is there? 4 milligrams. The total amount is going to be 4 plus 12 milligrams, or 16 milligrams. We'll divide out the milligrams. It's just 4 out of 16, or 1 to 4. Actually, not even 1 to 4 would not be the proper way of wording that. What would be the proper word of saying that? 1 out of 4. The reason we say out of is in this case, yeah, this 1 part is included within the 4. That's just one of the parts out of the 4. Up here, this 1 is not included in the 3. Those are totally separate ingredients. So that's why it's 1 compared to 3. 1, 2, 3. Down here, since the 1 is part of the 4, it's 1 out of the 4 parts. And then, of course, I can do the ratio of water to total. And that ratio would be, now I could go back and do 12 out of 16 and then reduce it. Or I could just look at this and say, hey, if 1 out of 3 parts is medication, or sorry, 1 out of 4 parts is medication, how many out of 4 parts must be water? 3. 4 minus 1 is 3. If 1 out of 4 parts is medication, the other 3 out of the 4 parts has to be the water. Does that make sense? Okay. By the way, this one here is what we call a unit ratio. The denominator is a 1. So we're comparing something to 1. A unit ratio gets used in certain applications, but it's not the common way. It's very common to leave ratios like this as 1 to 3 or 1 out of 4 or 3 out of 4. You cannot express this type of a ratio, by the way, as a unit ratio, because if it's out of something, you can't be out of 1 unless you have a decimal on top. So we said ratios always compare things that have the same units or same label. What if we have two things that have different labels that we can't change to be the same? For example, let's say you go for a drive and you drive 365 miles in 7 hours. There's absolutely no way I can change miles into hours or hours into miles. This is not a ratio. It is what we call a rate. So that's the first big difference between ratios and rates. Ratios compare two numbers with the same label. Rates compare two numbers with different labels or different units. The second big difference, we talked about a unit ratio where the denominator was 1. Not terribly common in ratios or not necessary in ratios. Rates are almost always expressed as unit rates. So to turn it into a unit rate, we're just going to divide by whatever the numerical value of the denominator is. The denominator, or the bottom number here, is 7. So I'm going to divide by 7. Well, 7 hours divided by 7 is just 1 hour. 365 miles divided by 7 is 52.142857143 approximately miles. Of course, we're going to round that, of course. But now you can see it's a unit rate because the denominator has a numerical value of 1. Now it's 1 hour. We still have to have the label there. A lot of times we hide that appearance of the fraction by doing this. Let's round this to the nearest hundredth of a mile. So 52.14 miles per hour. The appearance of the fraction now is pushed off so it only appears in the units. In fact, we often will hide it even further. We might say 52.14 mph. So that's still miles per hour. We need to be thinking this and actually ultimately this. But the units are, the fraction is hidden. For example, if you go on a trip and you get 23 mpg, what does mpg stand for? Miles per gallon. When you see that, you need to be thinking this. This is 23 miles per 1 gallon. Because you need it as a rate like that, as a fraction, to be able to calculate with it. So let's look at some examples of rates and ratios. Let's stick with rates first, since we're on it. We just looked at miles per hour. We saw that one. I'm going to look at miles per gallon. If you go on a trip and you get 504 miles and 24 gallons of gas, you have that rate. Now, of course, we would reduce that by dividing by 24. What's that going to give us? 41 miles? No, 21 miles. Over 1 gallon. Or 21 miles per gallon, or mpg, however you want to list it. Does that make sense? Can anybody think of any other rates that they see? One that I'm guessing many of you have been involved with. Let's say you work 25 hours and get paid $225. This is a rate. It's $225 out of or per 25 hours. I'm going to divide each of those by 25. 225 divided by 5 or 25 is $9. 25 hours divided by 25 is 1 hour. So that is $9 per hour. See, other rates. If you're looking in the medical field, you might run into rates like I'm supposed to administer 1,800 milligrams of medication over 4 hours. So you need to set what is the rate of that medication being infused into the patient. And if you're looking at an IV being dripped into the patient, that's 18 milligrams over 4 hours. Divide by 4, top and bottom, gives you 450 milligrams over 1 hour, or 450 milligrams per hour. Good question. How do you know which one goes on the bottom here? I gave the milligrams and hours. How do I know which one goes on bottom? Almost always, the bottom one's going to be a unit of time. If there is time, time's going to go on bottom.
So what about the gallons per mile?
Okay, miles per gallon, that's a tough one, right? Generally, you want the rate to be larger than 1. So in many cases, almost all cases, the larger number will go on top. And here's the key, is the units get used in calculations. For example, if I want to know how many miles I can go on 7 gallons of gas, if I am getting 23 miles per gallon, I want to know, okay, how far can I go on 7 gallons of gas? Well, this is basically a conversion. You're going to just multiply 7 by 23, exactly. Well, how do we know that works? Well, because this is 23 miles per 1 gallon. I'm going to multiply by 7 gallons, put that over 1. The fractions, the gallons cancel out, cross cancel out in the fractions. So that means we're left with miles. So we're getting a unit of 161 miles. So that gives us the desired unit. If that were gallons per mile, well, then it wouldn't work out. We wouldn't be able to calculate it like that. Now, again, that's the complex answer there. And you might be wondering, well, how am I going to know how it's going to be used later? You probably won't. So most of the time, you're going to have to either be told, or, like I said, if there's time goes on bottom. It's what goes on bottom is what would be the basis of calculating what's on top generally. So for example, in the medical field, again, let's say that medication is listed as 8 milligrams per kilogram. The reason it's 8 milligrams per kilogram is the kilogram is the weight of your patient, and you use that to determine how much medication you're going to give to them. And again, that would be, okay, 8 milligrams per 1 kilogram. You're going to multiply by, say you got a 60 kilogram patient. So the kilograms will cancel out. Any other questions? Let's look at some of those ratios. If we're looking at ratios, there's a lot of ratios out there that we deal with. In the mechanical side of things, this is where you get to use your imagination because I'm going to draw pictures. I'm horrible at drawing. So you better use your imagination. Everybody guess what this is? Those are gears. This is a gear ratio. Gear ratios go by the number of teeth. It's the number of teeth in the driven gear over the number of teeth in the driving gear. How many teeth are in this big gear here? Just count them. There are what? 12. How many teeth are in this gear? 8, hopefully. How do we know which one's the driven and the driving? Well, we need more information. Let's say I show you this. Pretend that looks like a little motor attached to that big gear. If I separate the two gears now, one of them will keep turning and one of them will stop. Which one will stop? The 8. That's the gear that's being driven by the other gear. That's the one that will stop. So that goes on top. That's the driven gear. So the 12 is the driving gear. It's the one that's forcing the other one to move. It is driving the other gear. We can reduce that by dividing both by 4. That is a 2 to 3 gear ratio. For every 3 teeth in the driving gear, there's 2 teeth in the driven gear. It also ends up describing their speed and all sorts of stuff. What if we have pulleys where we don't have teeth in them? Well, all that counting the teeth was doing was describing the size. For 2 gears to mesh together, the distance between teeth has to be exactly the same from one gear to the next. So by counting teeth, you're just describing the distance around the gear, the circumference of the gear. So for our pulleys, since we don't have teeth to count, we just give the diameter of the pulley. So let's say this is a 4-inch pulley and this is a 10-inch pulley. Again, I need to know which one is driven and which one's driving. So let's say I put the motor right here. If I cut the belt now, which one stops? The 10. So the 10-inch pulley goes on top. That is the driven gear. It's being driven by the other pulley. And the 4-inch pulley goes on bottom. It's the driving pulley. It's driving the other. It's forcing the other pulley to turn. So the inches cancel out. Both of those divide by 2, giving me a 5 to 2 ratio. Outside of mechanics, we go into construction. Construction side of things for a roof. You have roof slope. The slope of the roof, let's find, is a rise over a run. So let's say this roof is 24 feet wide. Height from top of wall to peak is 5 feet. The rise here is just this distance. That is the 5 feet. The run is not the 24. The run is the length of that sloping surface, which would be half the 24, the 12 feet. Well, the feet cancel out, so I'm just left with a 5 and 12 slope. 5 feet of rise for every 12 feet of run, or 5 inches of rise for every 12 inches of run, or 5 centimeters of rise for every 12 centimeters of run. The units don't matter when we're dealing with ratios. Outside of construction, if you're driving, I don't know if you've ever seen like signs beside the road that say grade, 6% grade or 7% grade. Like if you're on Highway 8 over by St. Croix Falls, there's a sign there, steep grade. That I believe is an 8% grade. What a grade is, it's the same thing. It's a rise per 100 feet of run. So an 8% grade is 8 feet of rise for 100 feet of run. And I'm not going to simplify that for just for grade. You wouldn't reduce the fraction. Okay. On the business side of things, if you ever go to get a loan, of course, you hear so much about credit scores. You got to have your credit score up to get good rates on your loan. The credit score generally does not determine whether you get a loan unless it's really terrible. If you've got like a 520 credit score, they might say, we don't think so. It might determine how much they allow you to borrow. But in general, your credit score, if it's above a certain number, at least, all your credit score determines is what interest rate they're going to give you. If you don't have the really good credit score, they're not going to give you the best rates. They're going to charge you a higher rate. What generally determines whether you get the loan or not, because the credit score doesn't determine your ability to pay, it determines your history of paying more. And what generally determines whether you get the loan or not is a debt to income ratio. A debt to income ratio is just that, what your monthly debt payments are compared to your monthly income. So let's say you get a job where your monthly income is $3,000. Let's say you have a car, so that's your income, so it's your debts. Let's say you have a car payment of $300. That's somewhat reasonable. I've had some that are definitely higher than that. Let's say you have credit cards of $200 to pay every month. Now, would they put in gas for your car and stuff like that? Insurance? No, those are not debts. Those are other expenses. You might have your student loan that you might be paying $100 a month on. And let's say that you are applying for a loan. You want a mortgage on a house. And that mortgage would be, what do I have there? $600. What would that make your debt to income ratio if they give you that mortgage? Well, I add up all my debts there. I have, $1,200 in debt per month. So that would give me a $1,200 of debt payment for $3,000 of income. Now the dollars divide out, they cancel out again. 1,200 and 3,000 can both be divided by 100. Give me 12 over 30. Both of those can be divided by 6. Give me a 2 to 5 debt to income ratio. The standard in the industry was always a 1 to 3 debt to income ratio. If you had $1 of monthly debt for every $3 of monthly income, or less than $1 of debt for every $3 of monthly income, you were usually good to go to make those payments. This one came out to be 2 to 5, which is actually slightly more than 1 to 3. So they most likely would not give you that loan. By the way, one of the reasons why they had the huge loan crunch in 2006, 2007, 2008 was because in the mid-2000s or 2004, 2005, they pushed up. They wanted to get more loans out there, so trying to stimulate the economy. So what they did is they pushed the standard from a 1 to 3 debt ratio to a 2 to 5 debt ratio. This is basically 33% up to 40% debt. And a lot of people end up, they couldn't afford their payments. Or when the economy turned down a little bit and they weren't getting as much overtime or whatever, their income dropped just a little bit, they couldn't afford those payments anymore. Other ratios we might run into. We talked about those medications. If you're mixing medications, there might be that ratio of 40 milligrams of medication to 200 milligrams of sterile water. So again, that's going to give us a ratio of 40 milligrams to 200 milligrams. The milligrams cancel out. Both 40 and 200 can divide by a lot of things. Let's do 10 and then zeros. That's 4 out of 20. Both of those can still divide by 2 would work. 4 works too. Gives a 1 to 5. So again, it's for every unit of medication, we're putting it in 5 units of water. Okay, so let's take a look at let's say you are hired to produce parts. You're going to be hired to produce 500 parts. You will be paid $3,000. Question is, how much are you paid per part? First of all, will this be a rate or a ratio? This will be a rate because I'm comparing parts to dollars or dollars to parts. I'm not really sure which one. Now here's where it comes back to your question. How do I know which one goes on top or bottom? Well, this is paid per part. Per part implies that the parts are on bottom and the dollars are on top, or the other numbers on top. In this case, it is dollars. So that's going to be $3,000 over 500 parts. If I divide that out and make it a unit rate, I divide by 500. $3,000 divided by 500 is $6. 500 parts divided by 500 is just parts. One part. $6 per part. If we have, let's say that you are going to be saving money for retirement. You save $80 in a week where you earn $400. You want to compare savings to what you earn. Your savings out of what you earn. Put it that way. Will this be a rate or a ratio? This will be a ratio because we're comparing dollars to dollars. And we wanted to compare savings out of earnings. This is one where just the larger number would go on bottom as typical. So you have $80 savings out of $400 of earnings. The dollars will divide out, and both of those actually can be reduced by 80. Gives you a 1 out of 5. So you save $1 out of every $5 you earn. Any questions? You produce 1,200 parts in a day. 150 are defective. Find, now this is parts to parts, so we're going to be comparing a ratio. The ratio of defective to good, that's the first one. Find the ratio of defective out of total, and find the ratio of good out of total. So I'll give you a couple minutes to do that in your notes. So for the first one, defective to good. How many defective parts are there? 150. How many good parts are there? It's not 1,200, is it? 1,200 is the total. So how do we find the good? 1,200 minus 150. So that's going to be 150 over 1,050. Now, of course, we're going to reduce that. Both of those can be divided by what? Don't be shy. 50? 150? Okay. We can divide both of those by 150. 150 divided by 150 is 1. 1,050 divided by 150 is 7. So the ratio of defective to good is 1 to 7. Now notice I did say 1 to 7 because the defectives are not included in the goods. They're totally separate categories within another total. So that is 1 to 7. The second one, defective out of total. How many defectives? 150. How many total? 1,200. Both of those can be reduced by 150 again. 150 divided by 150 is 1. 1,200 divided by 150 is 8. So 1 out of 8. Notice I use the term out of. It's 1 out of 8 because the 150 are included in the total. The defectives are included in the total. So it's 1 out of every 8. Finally, the third one, the good out of the total. How many good parts were produced? 1,050 out of a total of 1,200. Now, I'm not going to reduce this here. I'm going to come back up here and look at this. Out of this ratio of 1 to 8, or 1 out of 8, 1 out of every 8 parts is bad. How many out of every 8 parts would be good? 7. That's a 7 out of 8 ratio of good to total. So if I give you 2 out of 15 critical care patients, code each shift. What is the ratio of stable? By stable, it means they don't code. Patients out of the total. So what would the ratio of stable patients out of the total? Well, the total is 15, right? Is that 2 out of 15? Or the 2 are the ones that code. They're the non-stable patients. So how many would be stable? 13. 15 minus 2 equals 13 out of 15. If I tell you that the ratio of medication to total solution is 1 part out of 8. Find the ratio of medication to water. Looking at this ratio up here, so the ratio of medication to total solution is 1 part out of 8. How many parts of medication are represented in this ratio? 1. How many parts of water? This is the tougher one. How many parts of water are represented in that ratio? The 8 represents the total parts represented, correct? So the parts water would be 8 minus 1 or 7. So in this ratio, all 3 of those numbers are represented. That's not necessarily 7 milligrams or 7 milligrams. It's 7 parts out of every 8 parts. So the ratio of medication to water is 1 to 7. Very good. It is that time for a break, so let's go ahead and take a break. It's 4:21. Let's come back at 4:31 to start our second half.